From my perspective, today's topic, decarbonization or energy transition, brings up a host of related topics I don't really hear being discussed publicly or detailed in our energy policy. It's clear there's a consensus surrounding the climate debate that finally has governments and businesses taking action. That consensus includes targeting the burning of fossil fuels as the main cause and also naming carbon dioxide as the biggest culprit. The goal of reducing carbon emissions is widely referred to as decarbonization. After all the discussions about semantics or terminology, I think the way we're going to mitigate climate change is to electrify the global economy. And of course, transitioning away from fossil fuels to renewable power is how we plan to get there. It's important to understand that by electrifying the global economy, we'll be transforming modern life into something very different than what we experience today. The energy systems we want to replace are currently ubiquitous around the world. To be successful at this scale, it makes sense to do so with a coordinated global response. However, what we see happening is that pretty much every city, state, county, and nation is crafting their own plans. Those able to transition at a massive scale will likely set the standard for the rest of the world. At the same time, the exponential demand they place on the global supply chain may impact smaller economies' access. At SEH, we believe assessing what the rest of the world is doing needs to be part of the conversation as we prioritize our electrification strategy here at home. My goal is to illustrate why electrifying even a small economy like Hawaii's suggests including metrics beyond carbon emissions and the speed at which we transition. To begin with, we know the Hawaiian Islands are the most remote inhabited location on the planet and small by any standard. We also know that Hawaii is dependent on the rest of the world for 90% of what keeps its economy running. History has shown that institutional change here is a very slow process. That makes the task of expanding our own clean energy goals quite challenging. This last point leads me to ask a few questions. Are Hawaii's energy policies in sync with those being implemented around the world? Are they flexible enough to support the development of an entirely new energy landscape and do it with the urgency required by law? Can we execute this energy transition and sustain a local economy that investors expect to keep growing? So speaking of the economy, maybe we should define what an economy is. It's important to understand that within any economy, energy is the master resource. It's also important to understand that while energy can't be created or destroyed, it is constantly being converted from one form to another. Physicist and economist Robert Ayers described the essence of an economy like this. An economy is a system that extracts, processes, and transforms this master resource, energy, into products and services. That means nothing gets done in an economy without consuming energy at every step along the line. The graph you see here plots 50 years of global energy consumption against its corresponding GDP. The correlation variation between the two is less than 1%. Given this, it's reasonable to conclude that economic performance directly corresponds to the energy consumed by it. Energy is the input, the value of the economy is the output. Therefore, if an economy consumes more energy, it tends to grow. Conversely, it's reasonable for the opposite to be true too. As we dive further into this presentation, I think this is an important connection to keep in mind, especially if our plan is to replace where much of that energy comes from in a little more than 20 years. So the big question is, can intermittent wind, solar, and battery systems we see being deployed at an exponential rate deliver enough power to meet our existing needs, as well as to deliver the power we know will be needed to electrify light-duty transportation, industrial transportation, and the heat-intensive industries like steel, cement, petrochemical refining, and food processing? Our energy reality is this. Modern civilization exists as a continuous economic activity, and the flow of energy is how and why. Right now, 3/4 of the global economy's energy is derived from fossil fuels. And among those fossil fuels, the liquid fuels that serve as the lifeblood of modern just-in-time logistics has no replacement at scale, nor is there one on the horizon. For me, seeing the scale of these logistics is really a stunning experience. This is a snapshot of maritime traffic moving the global economy from one end of the planet to the other. This is another snapshot, but this time it's global air traffic. It's the norm to find 20,000 commercial aircraft in the air at any one time and average more than 100,000 flights a day. In July of this year, we saw more than 134,000 flights set a new single-day record. But wait, there's more. Those numbers don't include military, private, or cargo flights. Again, all of these are powered by liquid fossil fuels. This is what the global rail system looks like. The freight market grew by 5.6% in 2022 and is forecast to continue growing at a rate of 5% per year through 2027. In total, 95% of global transportation energy comes from liquid fossil fuels. We hear a lot about what electrifying light-duty transportation will do to reduce emissions. Progress in that direction is really just getting started. In 2021, less than 1% of light-duty vehicles in the US were fully electric. That's definitely changing, though. EV sales grew in the same period to 5% of all new car sales and had grown to nearly 7% of total market share by January of this year. Combined, light-duty vehicle sales were either hybrid, plug-in hybrid, or electric. Even with this growth, the EIA still projects less than 10% of the total light-duty fleet will be EV or PHEV by 2035. Today, with virtually all transportation powered by liquid fossil fuels, maintaining our current economic activity and decarbonizing at the same time means replacing that energy with portable fuels that start out as clean electricity. That will require, this is on a global basis, by the way, this will require terawatts of renewable power on top of what's needed to replace the non-renewable power we use today. The leading candidate to serve as the building block for these carbon-free liquids is electrolyzed hydrogen. But it's not just making the hydrogen or generating the initial power to produce it. It also means producing an entirely new interconnected distribution network while keeping our existing system functional as we build its replacement. So now, having a more detailed sense of the task at hand, let's ask this question again. Can the world achieve meaningful decarbonization at the same time it constructs a replacement for the existing fossil fuel system and keep the global economy running at speed too? To help answer that question, let's take a look at some more data. Our World in Data, the publisher of this graph, plotted energy consumption by type over the past 223 years. For fossil fuels, they have data for oil, coal, and natural gas. And for renewables, we have hydro, nuclear, wind, solar, biomass, biofuels, and other low to no carbon sources used to generate electricity. One thing that stood out to me was the exponential growth in fossil fuel use that's taken place since World War II, and that the adoption of modern renewables like wind, solar, and biofuels didn't really start to register until around 2005. With decarbonization becoming the primary focus for mitigating climate change, I wondered how much progress we'd made since 2000, a date prior to any real effort towards addressing climate change got going. From the data in this chart, I was able to create this spreadsheet comparison. So what I did was to look at the relationship between fossil and non-fossil fuel consumption in our total energy mix. First, I looked at their combined annual consumption in 2000. From there, I did some simple math and calculated the ratio between the two categories. I came up with 77% fossil and 23% non-fossil. Then I did the same for 2022. I was really shocked to see that the ratio was identical 23 years later. It hadn't even changed by 1% in more than 2 decades. Now, I immediately contacted my colleague who works for the Hawaii Natural Energy Institute and asked him to check my math. He got the same thing, so I felt a little bit better. So looking at more of the detail, I saw that there had been a 110,000% increase in solar deployment and a 58-fold increase in wind. Even with that exponential growth, solar's overall contribution to the energy mix was less than 2%. And with both solar and wind combined, it tallied up to just 5%. What will it take to achieve 20 or 25%? And again, this is on a global basis. Another striking observation was the overall increase in consumption over that period, 46% in 23 years. What's clear is that as of 11 months ago, the global economy isn't burning fewer fossil fuels. In fact, with that kind of increase, we're emitting more carbon than ever. This graph illustrates the measurable change in atmospheric CO2 concentration between mid-January of 79 and mid-January of this year. Nowhere do we see even a plateau, much less a decline. Seeing this trend and understanding the emissions goals Hawaii has set for itself, I wanted to ballpark what its proportional contribution to global emissions pencils out to. Data published in 22 for 2019 showed that Hawaii's petroleum consumption was slightly more than 47 million barrels that year. By comparison, global consumption for the same time frame was about 36 billion barrels, or around 100 million barrels each day. That means over the course of 2019, the oil Hawaii consumed was approximately what the world consumed in little more than 11 hours. For the purposes of this discussion, a reasonable conclusion would be that carbon emissions would track in similar proportions. Out of that oil consumption, about a third of it was used for power generation, meaning a year's worth of Hawaii's grid power emissions was produced by about 16 million barrels of oil products. That approximates what the world emits in about 3 hours and 45 minutes. And I don't mean this comparison to be rhetorical. While it may seem simplistic to some, I still see this kind of comparison being relevant, and I'll illustrate why as I continue. Looking at the implications that come with this analysis, quite a few questions come to mind. For example, given the urgency to combat climate change, why is the world consuming more and more fossil fuels? It's not like governments around the world don't understand the predicament we face. When I think about it, I'm pretty sure that within our economic system, those who invest in it and govern it believe growth is essential. And without that growth, their venture is failing. As we've seen, growth always involves increased energy consumption. What else are they going to use? Okay, so hypothetically, let's take the predicament of climate change to an extreme and imagine what would happen if the world stopped consuming fossil fuels today. I see reports where thousands and thousands of people would say, do it in a heartbeat. Obviously, we're not going to do that. However, it does open up the possibility that if the world doesn't decarbonize at the same rate Hawaii does, and knowing we're not able to move the climate needle on our own, maybe we have the flexibility to consider things like long-term systems resilience or economy-related opportunities as potential outcome goals. For example, it might make sense to model the scale a distributed intermittent system would need to achieve to replace all our grid power and on each island. How much power would we need to produce the volume of clean liquid fuels we forecast? And how do we do that within varying economic scenarios like domestic-only production or export scale production? Maybe we could also compare firm baseload power generation systems and their life expectancy with those of intermittent systems. We know the capacity factor, flow rate, and footprint issues fare far better with these systems than with intermittent. Another factor that could be modeled is whether the exponentially growing raw material supply chain for solar, wind, and batteries will remain economically viable when the time comes to replace components like battery backup systems. That could actually begin as soon as the mid to late 30s. And then there's the question that's often overlooked. What if carbon emissions isn't the only reason to electrify the global economy? This question specifically targets the economics surrounding liquid transportation fuels. We know petroleum is a finite resource that appears to be reaching the upper limits of its daily flow rate, especially as we now consume it at a rate of nearly 37 billion barrels each year. The reasons and exact timing of that limit are widely debated. We'll look at the subject in more detail later in the presentation. I think one of the problems surrounding our energy transition is public perception and understanding what renewable energy really is. Most people think that solar and wind farms are renewable energy. The fact is, renewable energy is not the same as the systems used to transform that energy into work. Solar panels are not renewable energy. Wind turbines are not renewable energy. Batteries are not renewable energy. The renewability of systems is not the same as the renewability of their energy inputs. Every system we deploy capable of transforming renewable energy into usable work requires fossil fuels to mine, refine, smelt, manufacture, and to transport around the world. And once again, liquid fossil fuels serve as the critical link in that supply chain. It bears repeating, there simply is no replacement for petroleum at an industrial scale, nor is there one in sight. Let's consider today's renewable energy system supply chain. If we accept that petroleum is part of every process, it's important to remember that the supply chain for every renewable energy system starts with mining. In recent years, we've seen supply chain issues blamed for countless delays in delivering products the market wants. These are some recent headlines reporting supply chain challenges. They range from cost issues to geopolitics to materials shortages. What can we expect from the renewable energy supply chain going forward? Is there a backup plan if mining and refining and manufacturing systems can't meet the demands of our climate goals? As the world transitions from fossil fuels to renewably generated electricity, how confident are we that upstream systems production can reliably keep pace with the exponential demand growth? This graphic illustrates the growth rate CRM mining needs to achieve to meet 2050 climate targets. As you can see, the steepest slope in the curve occurs within the next 5 to 10 years. What follows will illustrate one of mining's biggest challenges. Here we see a list of where all the critical raw materials needed to manufacture solar panels and wind turbines and batteries originate. One thing that stands out to me is how many of those materials considered critical are mined within China's borders. When considering geopolitics and China's influence over CRM, we have to remember that in addition to their own resources, China's been buying up rare earth mining rights across Africa, including Guinea, Zambia, South Africa, Zimbabwe, and the Congo. China also produces about 80% of the world's gallium and about 60% of the world's germanium, materials that are critical to the manufacture of semiconductors. Once materials have been mined, they still need to be processed and refined to satisfy varying degrees of purity. After processing, they're transported and made into components, transported again, where they're ultimately integrated into larger, more complex systems, which are then transported again. As we can see, China again dominates CRM processing for both renewable energy systems and EVs. They also command a significant portion of components manufacturing and systems integration. I think it's fair to say at this point, most of the world is looking at solar voltaic systems to generate its clean electrical power. Solar-grade polysilicon is the primary material that enables these systems to generate power. Today, 75% of the world's processed polysilicon comes from China, as do 80% of the completed panels. These systems are increasingly being deployed along with grid-scale battery backup systems. Again, these backup systems use many of the same raw materials as EVs. The IEA forecasts the existing global EV fleet of approximately 26 million vehicles will more than double to 60 million by 2026. SEH has a working relationship with a research scientist, Dr. Simon Michaud. With his PhD in mining and natural resources, he's been exploring just these kinds of scenarios at the Geological Survey of Finland, also known as GTK. The data you see here is part of his work GTK has been publishing. What's shown here represents estimates for the quantities of selected high-demand CRMs needed to produce one global-scale deployment of renewable energy systems capable of phasing out the use of fossil fuels. Its scope is based on raw materials component data present across today's functional, scalable, renewable power generation and storage systems. This is an exercise to establish the magnitude of what electrifying the global economy will require in terms of natural resources. As you can see, the metals selected are listed on the left, with estimated task-specific quantities for each. Those estimates are based on current fossil fuel energy consumption data, and then are converted to give us the renewable system equivalents needed to produce the same usable energy. These calculations include efficiency gains that arise when using electricity versus combustible fossil fuels to deliver the same usable work. The quantities listed in the first column is the volume of metals required to produce that one single generation of renewable energy systems. The center column of numbers represents the known volume of global reserves that are yet to be mined as of 2022. The column to the far right is the ratio between what's needed and what's available. Even if these numbers are off by a factor of 500%, generating enough renewable energy to maintain the existing global economic output without using fossil fuels seems unlikely. Keep in mind that this scenario only produces one generation of renewable energy systems. All these systems will need to be replaced on a regular basis. Even with expanding mine development investment, historically, for every 1,000 mineral deposits discovered, only 1 or 2 become mines. The time taken to develop a discovered deposit into an operational mine takes about 20 years. Then there are the economics and mining ventures. For every 10 producing mines, 2 or 3 will either lose money or shut down. As we discussed earlier, there's the critical matter of the liquid fossil fuels we use to move the global economy from place to place. Among them, rail is currently the most electrified mode of transportation. According to the IEA, 45% of rail transport was powered by electricity in 22, making it the easiest mode of transportation to decarbonize further. Maritime shipping and commercial aviation will be significantly more difficult to electrify. Again, hydrogen is the prime candidate from which to produce clean, liquid transportation fuels. Challenges there include how to reliably source the volume of clean electricity needed, and critically, the equipment that can use these new fuels. Those haven't been built yet. Each year, Rystad Energy, a well-respected global energy analytical company based in Norway, consolidates the data published by the IEA, the EIA, and the BP Statistical Review, and then issues their own assessment. In each of the last 2 years, the data showed that recoverable oil reserves contracted by 9% year over year. That's not what was consumed. It's what remains to be extracted within economically viable parameters. They go further to suggest that by 2050, the daily flow rate of oil will be half of what it is today. They also offer an upside, which is by burning half of what we do today, carbon emissions will be significantly reduced. If accurate, that will also impact the size of the global economy. JP Morgan Commodities foresees a similar trend as Rystad does. As you can see, they illustrate that within the widening gap between the black demand line at the top and the flow rate bands below. If history holds true to form, which Morgan seems to believe is the case, the impacts of what we've termed a supply deficit will likely be felt across the wider global economy with higher costs. In conclusion, it's not hard to see a similarity between energy consumption GDP and the atmospheric CO2 trend lines we saw earlier. As we pursue climate mitigation strategies, it seems reasonable to accept that energy, the economy, and the emissions that come from them have maintained a clear direct correlation to one another through the last half century. What I see baked into this data is a world that's in a predicament, and predicaments have outcomes. Those outcomes will likely change life as we've come to know it, versus this just being a problem we'll be able to fix. How we adapt to this predicament will be a defining factor for all who live here. When it comes to the future of energy, Hawaii is blessed. We have options most of the world does not. We can make decisions that might help us minimize the undeniable impacts of climate change, diminishing natural resources, and what looks like an inevitable economic contraction. We have the option to develop baseload power systems from geothermal heat, an indigenous resource that can deliver a lot of power. In doing so, we might be able to transition from a tourism and military-based economy to one capable of exporting clean energy to part of the world that faces much greater challenges than we do. Making these decisions will not be easy. They will be controversial, and time to make them is not on our side. Whatever we would do will require some well-informed, honest, and determined leadership. Mahalo.